Welcome to EPG Pathshala. Now, in this paper, the odds ratio is something which will come up in many of the modules. So this is kind of a summary measure module on the odds ratio. The odds ratio is kind of a fundamental measure of association when we have a binary outcome. The exposure variable or the risk factor of interest could be binary, could be categorical, or could be continuous. There could be a single exposure or multiple exposure. In each case, we are able to define the odds ratio. So in this module, we will define the odds ratio, see how it is estimated in the simplest case when we have a 2x2 table, look at its interpretation, how to test its significance, and then we will move on to slightly more complicated settings where we will see that even if we have multiple covariates, where some of them may be continuous, some of them may be discrete, it is no longer possible to extend the idea of the 2x2 table. Or even if it is possible, it is quite complicated and there is a heavy penalty on the sample size. However, the idea of logistic regression, which returns the odds ratios as an output, is quite easy to extend, and this is one of the reasons the odds ratio is very popular in the literature. We shall also briefly look at the latent variable formulation, which motivates the use of the odds ratio as compared to other competing regression models which you may have heard of, such as the probit regression. Finally, we shall see that in settings where we have contingency tables which are slightly more complicated than the basic 2x2 table, there are alternative definitions of the odds ratio depending on whether we look at the marginal, the joint, or the conditional distributions. In a subsequent module on Simpson's paradox, you will see that these odds ratios do not always give the same kind of interpretation and may lead to different conclusions about association. Learning objectives for this module. To begin with, we will define the odds ratio initially for the simplest case of a 2x2 table and later for more complicated settings. We shall look at its properties, which are all asymptotic. We shall see that there is a connection between calculating the odds ratio and fitting a logistic regression model to the data. And finally, we shall see that there is a latent variable formulation which justifies the use of the odds ratio from a subject matter point of view. The odds ratio, here is the simplest kind of table, which is a 2x2 table. So we have patients who were randomly allocated to one of two treatments, which could be placebo or could be aspirin. In each group, we observe the incidence of myocardial infarction. That is, we look at the number of people who had fatal attacks, non-fatal attacks, no attack. So this is a 2x3 table per se, but for the sake of analysis, we shall club two of the columns and reduce it to a 2x2 table. For more analysis of this data, you can look at further discussion on this case study, which has been taken from the Physician's Health Study and which has also been reported in the book by Agresti. When we define a contingency table, there are several distributions which we have in mind in the sense of probability distributions. So if pi ij denotes the probability of an observation being contained in the ijth cell of the table, we can define the joint distribution, which is specified by pi ij, I equal to 1 to capital I say, and j equal to 1 to capital J. Here we are assuming that the contingency table has I rows and j columns, and of course summation over ij, pi ij is equal to 1. We could ignore one of the sources of classification, that is, we could either ignore the rows or the columns and sum over them and get the marginal distributions. The marginal distributions are specified by pi I plus equal to summation over j pi ij, which is summed over the columns and gives the marginal distribution across the rows. Of course, summation pi I plus over I is equal to 1. Similarly, we can define the other marginal distribution pi plus j equal to summation over I pi ij, which is the marginal distribution across the columns. We can also define the conditional distribution, that is pi j given I, which is the probability of an individual lying in the jth column, given that we know that that individual is contained in the ith row. So obviously pi j given I is given by pi ij by pi I plus. In a 2 by 2 table, the simplest situation is that we wish to compare two proportions. So considering the aspirin example, we might wish to look at the frequency of fatal attacks for those on placebo and for those on aspirin. Now, strictly speaking, we are interested in the conditional probabilities, but for the sake of simple notation, we shall use the notation pi I to denote pi 1 given I. There are several measures. Two measures which you might have seen before are the risk difference, pi 2 minus pi 1, the risk ratio or relative risk given by pi 1 by pi 2. But for this module, we shall concentrate on another rival measure, which is called the odds ratio. The odds of an event is denoted by omega equal to pi over 1 minus pi. So for example, we might talk about a 40% chance of failure, or we might say that there is a 40:60 odds of failure. The odds is obtained by dividing the probability of the event happening divided by the probability of the event not happening. Of course, pi and omega are one-to-one functions of each other, and we can obtain pi as pi equal to omega by omega plus 1. The odds ratio is then defined as the ratio of the odds in the two categories. So, omega 1, for example, would be pi 1 over 1 minus pi 1, that is the odds of a fatal attack in the aspirin group, and omega 2 would be pi 2 over 1 minus pi 2, which is the odds of a fatal attack in the placebo group. If we divide these two, then we get the odds ratio of a fatal attack, comparing those on aspirin to those on placebo. The odds ratio is often called the cross product ratio. So assuming that we have sampled from the joint distribution, the odds ratio is given by theta equal to pi 1 1 by pi 1 2 divided by pi 2 1 by pi 2 2. Or on manipulation, this becomes pi 1 1 pi 2 2 by pi 1 2 pi 2 1, and from here you can see the justification for the name cross product ratio. The corresponding estimator theta hat is given by theta hat equal to n11 n22 divided by n12 n21. That is, it is the product of the frequencies in the diagonal cells divided by the product of the frequencies in the off-diagonal cells. You can satisfy yourself that the theta hat, which is denoted on this slide, is actually the maximum likelihood estimator of theta. So we go back to the aspirin data example and we reduce it to a 2 by 2 table, and from here we can see that the odds ratio is given by 189 into 10933 divided by 10845 into 104, which turns out to be 1.83. We could also have obtained the risk ratio from this table. So the risk ratio and odds ratio are related by the fact that the odds ratio is equal to the relative risk into 1 minus pi 2 by 1 minus pi 1. So the odds ratio would be exactly equal to the relative risk. If pi 2 is equal to pi 1, That is, if there is no association between the two factors which denote the rows and the columns of the contingency table. There is another situation where the odds ratio and relative risk are not exactly equal but are equal for all practical purposes. This happens when pi 1 and pi 2 are very small relative to 1, so that the ratio 1 minus pi 2 over 1 minus pi 1 is approximately equal to 1. So pi 1 and pi 2 being very small means that the event which we are concerned with is a rare event. An advantage of the odds ratio is that it can be used for prospective as well as retrospective designs. So normally we sample from the distribution of y given x. So for example, here it would be normal to allocate the two groups to aspirin and placebo and then look at the incidence of non-fatal attacks or fatal attacks in the two groups. However, a retrospective design would initially select a few who had fatal attacks, a few who had non-fatal attacks, and go back in time to see how many of them had consumed aspirin and how many of them were on placebo. An advantage here is that the odds ratio is invariant to study design. This means that the odds ratio which is obtained from sampling from probability of x given y is the same as the odds ratio which is obtained from sampling from y given x. This can be shown using Bayes' theorem. The implication of this is that when we have a retrospective design, we can ignore the fact that it is retrospective, and if our sole interest is on obtaining the odds ratio, we can calculate this as if we had a prospective design. Now note that this is not a property which is shared by the risk ratio or the risk difference. Estimation of the odds ratio, as I said, the maximum likelihood estimator of the odds ratio is given by theta hat equal to n11 n22 divided by n12 n21. Now it often happens that when we have contingency tables that we have some zero frequencies, and in that case the recommended procedure is to add 0.5 to each of the cell frequencies. So in this case theta hat is equal to n11 plus 0.5 into n22 plus 0.5 divided by n12 plus 0.5 into n21 plus 0.5. The standard error of the odds ratio can be obtained using the delta method. Now as you know, the delta method states that if we have a statistic Tn such that square root of Tn minus theta tends in distribution to normal 0 sigma square, then for a reasonably well-behaved function g, square root n into gtn minus g theta will tend in distribution to normal 0 g dash theta whole square into sigma square. Using this delta method, we can calculate the standard error of the odds ratio. Actually, we can see that if we take the log of the odds ratio, then it reduces to a linear combination of proportions, and it is easier to calculate the standard error. So if g pi hat is log of pi hat over 1 minus pi hat, then root over n log of pi hat over 1 minus pi hat minus log of pi over 1 minus pi will tend in distribution to normal 0, 1 over pi into 1 minus pi. Now note that the two rows of x are independent, and hence for the odds ratio we can obtain the standard error by taking the square root of the summed variances. There is no covariance term, and hence the standard error of the log odds ratio turns out to be 1 over n11 plus 1 over n12 plus 1 over n21 plus 1 over n22 whole to the power half. Now sometimes we have multinomial sampling, and in this case also we can get the standard error of the odds ratio using the multivariate delta method. So now there will be a covariance term, and it is possible to show that the formula generalizes to standard error of log odds ratio equal to summation over I summation over j 1 over n pi ij whole to the power half. Inference is now straightforward once we have obtained the maximum likelihood estimate and its standard error. At the simplest, we could perform a Walls test, but we could also perform two other likelihood based tests, which are the score test and the likelihood ratio test. The tests can be inverted to get confidence intervals, and another very common tool in the case of contingency tables, which actually also stems from likelihood theory, is the Pearsonian chi-squared statistic. Now let us consider logit and probit models and see what connection they have to logistic regression. So here we consider a class of binary response models of the form probability y equal to 1 given x equal to g of beta 1 plus beta 2 x2 plus beta k xk. That is, we have k minus 1 covariates which are x2 to xk. We include an intercept, and then the term within parentheses, which can be written more compactly as x beta, is the linear predictor and measures the total effect of all the covariates. We wish to relate this to the probability of y equal to 1, and we can do this using a link function capital G. So G, of course, has the restriction that 0 is less than gz, less than 1 for all z. An easy choice of G which would satisfy this requirement is any cumulative density function. So if G is a CDF, then probability of y equal to 1 given x would tend to 1 as x beta tends to infinity, and it would tend to 0 as x beta tends to minus infinity. A common choice is the logit model. So choosing g x beta equal to e to the power x beta by 1 plus e to the power x beta, which you can see is the CDF of the logistic probability distribution, would lead to this logit model. So here on this graph, on the y-axis we have plotted the probability of y equal to 1 given x, and on the x-axis we have plotted the linear predictor, and we can see that the logistic regression model leads to an S-shaped or sigmoid shaped regression curve. So to get justification for this, we can use a latent variable framework. That is, we assume that there is some y star which is unobserved. The reason why this is unobserved is that it represents the net utility of whatever event is represented by y equal to 1. So say we are looking at people who buy cars as opposed to people who do not, and so y is equal to 1 indicates that the person has bought a car. Now in addition to y and the covariates x, we have also another unobserved covariate y star for this individual, which represents the net utility of buying a car. So an individual will decide to purchase the car if the net utility is positive. We do not observe the net utility, and all we observe instead is the variable y. However, we can say that the net utility is related to x prime beta, and it is possible to show that this leads to the logistic regression model. Inference for the logistic regression model, we can use the principle of maximum likelihood. You can see using the binomial likelihood that L of y given x beta is equal to product I equal to 1 to n g of x beta to the power yi into 1 minus g of x beta to the power 1 minus yi. Now let us see the interpretation of these corresponding regression equations. Suppose that we have only one single explanatory variable x which is continuous. Then we write down the regression equation for the two combinations, that is log of odds of y equal to 1 given x equal to any value small x is beta naught plus beta 1 x, and increasing x by 1 unit to x plus 1 and rewriting the regression equation leads to the formulation on the second line of this slide. If we take the difference of the two and then exponentiate, we can see that e to the power beta 1 is the odds ratio comparing the case x equal to x plus 1 to the case x equal to x. The important point to notice here is that by fitting the logistic regression, we have obtained the odds ratio. Now, in the case of a continuous covariate, it would not have been able to construct a table, or at least not naturally, without artificially classifying the covariate, and hence logistic regression is a way to generalize the idea of the table to the case where we have a continuous outcome. Now, suppose instead we have a binary explanatory variable, that is, we have one variable z which is equal to 1 if some event A occurs and 0 if the complement of the event occurs. Then, as before, we can write down the two equations for the case where z is equal to 0 and z equal to 1, and we can see that beta 1 is the log odds ratio for the event y equal to 1 comparing the cases z equal to 1 and z equal to 0. So, in this case, with the single binary explanatory variable, we can obtain the odds ratio in two ways. One is through the 2 by 2 table, and the other is fitting a logistic regression. In the 2 by 2 table, or in the simplest case, there is no reason to prefer one over the other, but it is very rare that in any practical situation we measure only two variables. So finally, let us consider multiple logistic regression. The situation here is that we have two covariates, x which is continuous and z which is binary, and in this case we can write out the equations in before and see that beta 1 can still be interpreted as the log odds ratio comparing the cases z equal to 1 and z equal to 0, assuming that the covariate x is kept constant. Similarly for the covariate x. In this module, we looked at various properties of a very fundamental measure of association, which is the odds ratio. So at its simplest, we saw that the odds ratio arises as a measure which competes against the risk ratio and the risk difference in a 2 by 2 table. However, the odds ratio has some properties which are not enjoyed by the risk ratio and the risk difference, and the most important property is that it is invariant to study design. So this means that it is possible to calculate the odds ratio from a retrospective design, whereas it is not possible to calculate the risk ratio or the risk difference from such a study design. However, the odds ratio and risk ratio are often close, and this happens in the case when we have a relatively rare event. Next, we defined the logistic regression model and saw that there is a connection between logistic regression and the odds ratio. That is, in the simplest case, when we have a 2 by 2 table and we fit a logistic regression, we recover the odds ratio as an output. Now, in the simplest 2 by 2 setting, there is no reason to prefer the fitting of a logistic regression model as opposed to the calculation of the odds ratio. However, in slightly more complex settings where the explanatory variable is continuous, or we have a set of covariates where some are discrete, some are continuous, there is no obvious or easy way to extend the idea of the 2 by 2 table, and it is relatively easy to extend the idea of logistic regression. So for the multiple regression model also, we can see that the coefficients represent log odds ratios, assuming that all other covariates in the model are held constant. In a subsequent module, we shall see that It is possible to define multiple odds ratios depending on whether we look at marginal or conditional or joint distributions, and in fact we shall see that this can often lead to a paradox, which is well known in the literature as Simpson's paradox.